again, let's see, what did we do last time? We considered a matrix model. There is a single matrix we integrate over, and so we call it a one matrix model. Then we add exponential of minus 1 over g squared, and then we have trace. We can have our kinetic term, 1/2 of m squared, plus, and then we could have some general potentials. We could have some T3 m cubed plus some T4 m to the 4 plus dot dot dot. And then we treated this in perturbation theory by bringing this guy down from the action, and then we compute expectation value of stuff like product of traces of m to some powers and I. Maybe they appear some trace a given number mi of times in the Gaussian theory. This is better. Okay, so then we would multiply, we would compute, we would have to compute this expectation value. I would make a product from n equals 3 up to infinity of some objects like this, right? So when n, we did a few cases where we only had n equals 4 once, so this m would be 1 for m4 and 0 for everyone else. And we did one case where we did 2 traces of m cubed, so this guy would be 2 for n equals 3 and 0 otherwise. But then these guys, then we would compute by just doing some weak theorem. And when we did it, we saw that planar graphs have more faces, also called loops, and therefore they dominate. Okay, so let's try to see this in general. So let's try to work out the contribution from a given contraction like this. So let's consider now a general diagram, a general graph. Now, for a general graph, what would we have? Let's work out the general power of counting and so on. Well, first of all, if we have, each time we bring down a vertex, we pay a factor, 1 over g squared to the number of vertices. That's v. All right? Then each time we have a propagator, we have an edge, we get a propagator which is a factor of plus g squared. So we get g squared to the power of number of edges of the graph. And what about faces? Each time we have a face, we get a factor of n, right? Each time we have a face, we get n to the number of faces or loops of the graph. Now, here comes an important fact, which is that there is a relation between these three numbers that goes like this, that the number of vertices plus the number of faces minus the number of edges of a graph is a topological quantity that's called the Euler characteristic that measures the genus of the graph. And so this quantity is equal to twice minus twice the genus of the graph, where this genus of the graph is the minimum genus of a surface sigma, where we can draw the graph. Right? Of course, if the graph is planar, I can also draw it on a donut, right? But so the sphere would be the minimum genus. But if the graph needs a donut to draw, I cannot put it on the sphere. So the donut is the minimum. Of course, if I can draw it on a donut, I can draw it on a donut with genus 2. So the genus of the graph is always the minimum genus we can put. This quantity here is what is called the Euler characteristic. And people normally call it chi. Let's just do a check. Let's draw a cube. Did everyone reach this part of the tutorial yesterday where you were asked to think of a cube? So let's... Did everyone do this part? Who reached the cube in the tutorial?
There's no cube.
There's no cube in the tutorial?
There's lots of a diagram with a concept.
Ah, okay. Good. So this cube, let's imagine this graph. This graph, clearly I can draw it on the sphere, right? I can just put the sphere and put the points, the 8 points on the sphere and just draw the lines, right? So of course we can put it, we can embed this on a sphere, right? I'm not going to try to draw, but it's just you put a cube inscribed on a sphere. So you can draw it. And let's count the number of vertices plus faces minus edges. Number of vertices, you have 8. All right, so 8 plus number of faces, you get 6. Minus number of edges, you get 12. 4 plus 4 in the bottom plus 4 on the sides. And this is indeed equal to 2. And because we have genus 0 there. Okay. How would I draw a graph that would correspond to genus 1? What would be the simplest way of drawing a graph like the cube but for genus 1? Well, the simplest is maybe one of the ones that we drew yesterday. But more in this spirit of Platonic solids. What would be a simple solid that would look like genus 1 instead of the cube? How would you transform a cube into a genus 1 surface? Let's put a hole in the cube. So how would you put a hole in the cube? Let's draw the cube. And how would you put a hole now?
Like a cylinder.
Cylinder, I don't like cylinders. Cylinders have round edges with straight edges. A square at the top and the bottom. Oh, we could... what's your name? Sorry? Kelly. As Kelly is proposing, we could do a square here, right? That would go here. And this looks like a nice genus 1 surface, right? It's a cube with a hole in the middle. So is this statement familiar to everyone? Who knew this statement before? This simple statement in topology. Almost everyone knew it, right? Okay. Who did not know it before? Okay, everyone knew it. So can you do the counting here and tell me what you get? Who said 0? Did you do the counting or you knew? So tell me, Charlie, right? Yes. What's the counting? Tell me the number of vertices.
So it should be the same as the cube, but you're reduced 2 because the inner cube doesn't have the top and bottom faces.
Number of vertices. So you are making an argument for the full result. Yeah. Right, but I would like the counting. I would like the number of vertices, etc. So how many vertices does this object have?
16.
16, good. plus how many faces?
12.
Is it 12? 4, 5, 6, 7, 8, 9, 10. 10. 10.
It's 2 cubes minus the 2 faces. So.
Edges. How many edges?
26.
Twice as many as a cube.
Twice as many as the cube, right? 24. Right? My God. Got a problem.
For some reason, I feel like we can't count the top and the bottom as faces.
Do you have to add 2 edges to connect the 2
Yeah, we have to
faces?
connect.
Yeah. Good. Maybe that could be the answer. Why do you think that would be the case?
They're not like the other ones. They've got a hole in the middle.
Exactly. Exactly. Sorry, can you remind your name again? Sorry. Yeah, as Kelly pointed out, the theorem says that these faces, when you do these faces, they must be contractible. The loops, they cannot have holes in them. Okay. And so here it will not apply. So let's make it apply. So what could we do to make it to make this shape into something where it would where this would apply? We could, for example, I don't know, lift this a little bit so that we would add some extra vertices here, right? Right? Now it's lifted a little bit, right? So we make like a small truncated pyramid on top. Now each face here is contractible. Kelly would be happier. And here we would lift a little bit. And now each face in the bottom is contractible. Right? And now if you repeat the counting, you scratch this. And you do the proper counting and you will get it. Okay?
Are you sure?
I am. I can leave it as exercise. So, how do we go about proving this relation before we go on and checking what's the implication? I think everyone knows about this relation. Few people know about simple proofs of this relation. So let me just show you one simple proof of this relation that I think is worth knowing. Maybe there are other simple proofs, but for me, this is my favorite one. So let me tell you. So suppose we have a graph that we can draw on the sphere. So here is a sphere, topologically. And then there is some graph that we can draw here. It could be something like our cube, or it can be any graph that you can draw on the sphere. Right? So it can be something, anything that you can draw on the sphere. It's an example, planar graph. Right? So this is an example. So here we want to show this relation for a planar graph. So we want to show that if you have a planar graph, we always get 2 on the right-hand side. Now, here is a derivation of that statement. Take this graph and make this graph with metal. And now, take your favorite vertex and insert some electric current here, I. And take another vertex, your favorite one, doesn't matter, and remove the current I from here. Right? So you pick your graph, you make it of pieces of metal, right? And then you inject current at one cusp, at one vertex, and you remove the current at some other vertex, right? And then electric current will flow through the graph from one point to the other. And we should determine the current, we can determine the current at each edge, right? So let's count variables and equations that we need to determine the current at each edge. So we will have E currents. Right? At each edge there is a current. We inject the current, we remove the current, so there are E currents. And so E currents is our number of variables. This is what we want to know. We want to know how many, what's the current at each point in the graph. And now let's see the number of equations. Right? So now we compare. We want to say that this is equal to the number of equations. Let's write the number of equations. So what equations do we have to determine this current? Right, so what to determine the current? So first,
One for each vertex for conservation.
at each vertex, we have conservation of current. How many equations that gives us? It's almost V, but not exactly V. V minus 1, because if you impose conservation at all possible vertices, at the last one it's automatic. All right? So we have V minus 1 equations. These come from conservation of current. All right? Plus, what other equations do we have?
Potential for phase.
Very good. At each phase, if you measure the total potential as you go around, it must be 0. And here you see why it's crucial, Kelly's condition, that you cannot have holes. All right? You need to make sure that indeed it's topologically trivial. And so now we have the condition that at each phase, so this is, if I have a phase, I start here, and my total delta V must be equal to 0 if I go around. And again, there is minus 1, right? The simplest, let's draw here a simplest possible graph. If I inject current here and I remove here, right? Again, momentum conservation, imposing here it's enough. And 0 potential, imposing here automatically outside is enough. Right? If I have 0 potential from here to here, I have outside as well. So also phases minus 1. The very last phase is automatic. Right? So these two guys need to be the same. And we are done. We conclude that vertices plus number of faces minus number of edges equal to 2. Right? And this now also generalizes to genus, because if you now have a genus surface, you have to further impose that you get no difference of potential around the 2 new cycles of the torus. Right? If we have a genus 1, now we have 2 extra conditions. Which are the absence of potential. This, if I measure the total difference of potential as I go around here, or if I measure the total difference of potential I go around here, the total delta V must be equal to 0. Etc., etc. Each time I go in genus, I get 2 more conditions for the 2 new cycles. And therefore, this 2 becomes 2 minus 2G.
What is the 2 extra condition? Is it already going along?
It's the fact that there is no difference of potential as I go around this cycle or around this cycle. These are 2 independent cycles of the torus. And each time I add an extra genus, I have 2 new independent cycles. And so the number of equations increases by 2 times the number of genus, and therefore we get a precise equation.
So, but also in this case where you said that the phase should be contractible, but for delta V to be 0, there is no condition of the phase to be contractible, right? You go along the loop, it will always be 0.
I think that one comes from current.
Okay, so maybe I said, okay. Okay, so this is the derivation. Let's see, where does it enter that the face needs to be contractible?
It's like if there was a hole in between and there was changing magnetic field, it could induce an EMF. But
Yeah, in this particular case, if there was a hole in the middle, right, this would be like two disconnected graphs from the point of view of this graph here, right? So if I don't put these edges, it's like I have the graph that is the outer cube and the graph that is the inner cube, right? And so indeed, from this argument, if I inject current in the outer cube, there will be nothing in the inner cube. So I will need to inject it as well, and then it will be like computing two planar graphs separately.
Maybe we can say every edge should be connected.
Right.
We cannot have two disconnected graphs.
Exactly. Good. Okay. Anyway, this was as you guys said, you knew this stuff already, so this is just for fun. Just we have a new derivation. Did people knew this derivation? Who knew?
You did that, so I.
Ah. I see. In Brazil, yeah, very good. Okay. Good. Okay, so let's go on with our general diagram estimate. So we are there. So we continue from here. Yeah, we are there. And so with our general graph, we conclude that our graph scales. Let me see, what do I want to do? So I just wrote again, n to the number of faces, g squared to the number of edges minus vertices. So I just copied what is there. And then, using that relation over there, I wrote this apparently as n to the 2 minus 2g. So I replaced f by 2 minus 2g plus that quantity. And then what appears here is g squared times n to the power of edges minus vertices. And so what's crucial is that you see that a graph that has some edges and some vertices, right? This is just the 't Hooft coupling lambda that is held fixed. And all graphs of the same topology come with the same factor of n in front. And that's exactly what we had observed, that we're getting that all planar graphs were proportional to n squared. And so we conclude that if I sum over all graphs, right, I can write this as a summation over the genus G, right? Then each genus G will give me some factor of n to the 2 minus 2g. And then I sum over all graphs of genus G. Right? And then that summation will come with some symmetry factor times lambda to the power e minus v. This is just some counting of how many equivalent graphs there are, like these 3, 9, and so on that we were getting. And this full thing here, now I could say, defines for me a function f that depends on the genus G, and that is just a function of the 't Hooft coupling. And so what we get is precisely as in a string theory. We get n squared times a function that describes all possible planar graphs plus n to the 0 times a function that will describe all graphs of genus 1 plus n to the minus 2 times all surfaces, all graphs that I need to draw on surfaces of genus 2 plus dot dot dot. Okay. Now here, actually, I'm kind of implicitly assuming that I sum over all connected graphs, right? At least in these pictures. I never drew a sphere times a sphere. So let's actually be precise. Let's say that here we sum over all connected graphs. Right? And then what would this quantity be? What should I put here so that I really have an equation? What function would this be? What should I put here? Well, let me remind you, the quantity we defined was this integral here. This full quantity here, I did not give it a name, but let me give it now, is what we would call the partition function. Should I put z on the left-hand side of that equation? Not really, right? Because z, when I expand, when I bring down, say, trace of m to the 4, twice, right? I have the disconnected graphs. Why not? Right? So it's not z that I should put on the left. What should I put? Log of z, right? When you have z, a summation over all diagrams, you take logarithm to compute what's called the free energy, f, where f is log of z. So z is like a gas of strings. It has disconnected components, right? So it has a sum of all planar graph square, planar graph cube, etc. And so it's really a gas of strings. And f, the free energy, so we see this free energy, this is like a single string partition function, whereas this would be a gas of strings partition function. Take the log to kill the disconnected graphs as usual. And so this here is equal, becomes identified with a string theory expansion. With, if we identify this n with n to the power -1 related, being what you would normally call the string coupling. Right? In other words, this graph here, what happens to this? I need a probability of splitting the string, creating two strings, and then annihilating it again. So this graph should be G string square compared to this. Right? I need a G string to create those two strings, a G string to annihilate. This graph, I need to create, join, so G string to the 4 compared to this. And indeed, n to the 4 is the difference. Right? And so if I identify 1 over n with G string, it looks like this is automatically what I would expect for a string expansion. Now, let's check this string picture. Let's develop this string picture a little bit more in the remaining 20 minutes. So here, we conclude, in particular, that yeah, so let's make some tentative dictionary.
I have a question.
Yeah.
Why
can we make this conclusion when our target space is just a point? Don't we need like specific numbers of dimensions or other things for string theory to make sense? Why is this okay to think about it this way?
Okay. Yeah. So first of all, you don't know what the target space is at this point, right?
We assumed it's because we're not doing the or maybe today we implicitly.
No, be careful. We have 0 dimensions. They are mapped to a matrix M. M is the target space. What is M? M is an n by n object, not a point, right? So then the question is, okay, this M, the summations of all this matrix M, they define something that has the structure of a string theory. But to identify properly the variables, to say, is this M describing, what kind of dimension is this M describing, you need to work harder. You don't know a priori what's the target space of this map. So just to confuse you a little bit, let me give you an example. Suppose we have, instead of one matrix M, suppose I have 4 matrices. Mx, My, Mz, and M time. Right? Now we have a 4-dimensional target space. You would say that you have 4 components, x, y, z, and t. Right? And now you could do computations where you are still computing, say, you put some expectation value of some trace of m in the direction x 4 times, etc. And you compute some correlation function like this. And this topologically would look like you are considering some correlation function of some strings. Now, what exactly is the target space? Is it 4-dimensional as it indicates here, or is it 1-dimensional? The precise target space we don't know. I think at this point we need a better dictionary. You need to understand what are the dimensions. We need still to work out a little bit harder in our dictionary. Yeah. Wow. So what would be our tentative dictionary? So first, 1 over n, we said if this dictionary works with string theory, this should be related to the string coupling. The 't coupling, lambda, which is g square n, which, by the way, now we proved that this is the good scaling. Yesterday we had guessed based on the beta function that it was probably a good scaling. Today we proved it, right? Because we saw that the graphs do organize as functions of lambda for a given genus. What would this be the analog of? Remember that in string theory you have 2 parameters. The string coupling, that tells you what's the probability of string splitting, and the string tension, that govern the fluctuations of a string. Right? So this would be related to the string coupling because it's about splitting and joining higher genus. Whereas this 't coupling lambda, what would it be? If lambda is very small, the diagrams that dominate are very boring diagrams with very few loops. Right? The more loops you have, the more faces and edges you have, the more powers of lambda you have. As lambda starts increasing, you start to have more and more graphs that matter. And eventually you could imagine that you have some dense shapes. The surfaces become very dense and all graphs matter. Right? And so the picture is that as lambda is increasing, you are going towards a more and more classical string description where the string tension should be big. And you have some smooth surface. But as lambda goes to 0, the string tension should become very small and the fluctuations are very wild and you don't have some classical limit. And so it's still tentative. We are kind of arguing, but we would say lambda, or maybe some function of lambda, or lambda to some power or something like that, should be identified with the string tension. Right? And this would be the string coupling. Basically, the intuition here is that large T would mean some classical smooth surface that we kind of visualize as having a surface that is triangulated very, very much, right? Which is like some huge graph. And therefore, we think of this as coupling some big coupling, such that these big graphs dominate. Whereas small tension would mean that all surfaces matter and it's something very crazy, and then you could have some crazy small graphs dominate. Anyway, this is just some guesses. Everything here is hand waving at this point. We'll try to make this very rigorous next week. But then, what else do we do in string theory? What are the rules of the game in string theory? By the way, who had string theory? Who is not taking string theory and does not have string? Is string theory going on? Yeah, okay. So string theory is a theory where at this level of cartoons you are following, right? So there is a splitting probability, there is a tension probability, and in string theory what you do is you compute expectation values, say on a given genus, say genus 1, of what are called vertex operators. So you insert some vertex operators V, say some vertex operator V1, some V2, some V3, and then you compute expectation value of these vertex operators on some surface of genus G, and this is what describes the amplitude for these two strings going into one string. So there is an operator V1, V2, V3 that insert a string. And so we have this vertex operator V that inserts the string. And V, the vertex operator, creating a string. And the claim is that the picture here is that this should correspond to some local operator, like schematically trace of m to some power L. So this one is easy to see, so let's see this last one. Why do we say that these kind of objects create a string? So indeed, suppose we consider the expectation value of two of these guys, 1 over g squared, it's our favorite normalization, 1 over m to the L, 1 over g squared trace of m to the L. And here I'm doing it, you see I'm not putting a 0 here, so here I'm doing it in the full matrix model. Not in the Gaussian matrix model, in the full one. So what are we instructed to do to compute this in the full matrix model? We insert this operator, we insert this one, and then we bring down from the vertex the other interactions many, many times. Right? And we start drawing all possible graphs. Now let's first spend a few seconds drawing this graph here. We drew it last time and we drew it like this. But let me draw it in a few equivalent ways, and then we'll pick our favorite to say that this looks like a string propagating from one point to another. So this is one way of drawing this, that you follow the indices. If all you care is about following the indices, you can draw it like this as well. Right? You just open it up a little bit. 1, 2, 3, 4, just one more. Right? This is the same thing. I just blew it up in the middle so that I see the index a little bit better. And another way that I could use to draw this picture is I can just say the last and first index are the same, and then I could draw it like this. All these pictures would be the same. I need to keep in mind that this is one operator, this is one operator, and this full thing is one operator. I just keep track of the indexes. Right? And then we have the other operator and we need to contract them. Right? So let's try to draw it, and I'll try to draw it. We have a sphere, we have two punctures, so it's like a cylinder, like when we discussed CFT, that we discussed, right? A cylinder with a sphere with two punctures like a cylinder. So let's make that manifest. So let's use a representation like this for our first operator, and a similar representation for our second operator like this. And let's draw it, instead of putting the one point in the north pole of the sphere and one at the south pole, let's put them in, let's open up the sphere and make it into a cylinder. Did you get what I'm doing? So I have a sphere, and I put one of these guys at the North Pole. At the South Pole, I choose to put the other guy. Right? One guy at the North Pole, one guy at the South Pole, and then I just draw that sphere as a cylinder. So let's draw it here. If I draw that sphere as a cylinder, so I have the top of the cylinder where I have this index that I follow. I'm not sure if I'm going to regret drawing it in 3D, hopefully not. So here is the top of the cylinder. Then I have my cylinder, and then I have the bottom part of my cylinder. And then we have to draw the weak contractions that connect these operators, right? But also bringing down vertices and adding more vertex along the game. So let's start drawing this picture. So let's, for example, this line would want to contract with this line. Something like this. But maybe here, for example, you can connect with a cubic vertex. And here, maybe we can connect with some quartic vertex. We can meet some quartic vertex. This would be one diagram that would show up in some weak contractions, where you bring down from the action a quartic vertex and a cubic vertex, and you connect like this. And then this graph could connect here, and this could be, I don't know, another quartic vertex that would come from the action. And this guy here could do something, I don't know, like this, for example. It can meet some cubic vertices and do something like this. All these graphs, they must be planar if we are considering the leading order in N. So I need to draw them always on the surface of the cylinder. And then this line could just go here. Maybe it goes directly. Maybe it also meets some cubic vertex. And this one goes here. And it interacts here. Maybe at some point it goes to the other side. And now that it goes to the other side here, it could go on like this. And here it could meet this other guy. Continue going up. Right? And this line met this other one. And because this one is hard to draw, I'll just make it go up, connect there. And this line could then also just go down all the way and connect here. Maybe here at some point they choose to do this. And connect here. And here, these guys could just connect. And this is one graph with a few vertices. But as you imagine, as you put more and more and more vertices, this looks very much like starting with some string and summing over all possible shapes of the string that goes from here to here. So the idea would be that you take this thing and you sum over all possible diagrams that fill in the cylinder. And this would be equivalent to starting with a vertex operator here, putting another vertex operator for the bra, and integrating over the shapes of the string. At least in pictures it looks the same, right? I mean, summing over all possible diagrams would be not changing the topology is fixed, but integrating over the shape of the string. Right? Here we would have e to the minus the string tension times the action of the string. And so these operators, these traces, have the right topology to look like a string, like a closed string that we would insert. So here, this would be creating a closed string, not an open one, closed one. And then this object here would be inserting, creating the string. Right? So this is like a string coming in. And this would be like the string going out. Now, let's continue to see if this picture makes sense. What happens if I have not one string evolving, but two strings evolving? What would they do? If I have two strings evolving, to leading order, what would they do? If the coupling of the strings is very small, what do they like to do to leading order?
We go separately, they go separately.
They go separately. They just propagate separately and there's nothing special. So let's check that. So now here we saw that if I sum over all planar diagrams, in other words, all diagrams that fill in the cylinder, this would be equivalent to integrating over all genus 0 surface that connect the string to the string. Okay, so that's already one element that backs this interpretation. Now let's think a little bit about the two strings propagating. Now, if I have two strings, I would have one operator O1, O2, O3, and O4. Right? And we want to try to say that these two guys, okay, we just have this. Right? We have four strings, so we have four operators, right? We have two in the beginning, two at the end. Now, this diagram here, connected, scales as what? If I have a connected diagram, we saw the general scaling of a general diagram, right? So the planar one, the connected one, scales as, it's there, right? N squared. Okay. Any connected diagram that I draw on the sphere scales like N squared. What about, but then the correlation function, O1, O2, O3, O4. If I write that this could be some disconnected parts, O1, O2, O3, O4, for example, plus connected, right? Where these guys would be now connected. Now, I could have a priori, you could say it could be 1, 2, it could be 1, 3, it could be 1, 4. I could have all possible pairs. Let's suppose we forbid that. For example, let's suppose that we make this O1 and O2 be some trace of some M to the L. It's going to make it a mess. Okay. Plus other pairs. Okay, fine. We can have other pairs. But then we have the disconnected part and the connected part. Now, how does a connected diagram scale? Any connected diagram, N squared. And so we conclude that this gives me N to the 4 times the disconnected contribution, where I have just the two strings propagating. And if I put a parenthesis here, plus the connected diagram, which would now come with a 1 over N squared times the diagram where they would interact in a connected way like this. Do you agree? And so precisely we identify that this 1 over N squared is indeed what we said before, G string squared. There is a probability of annihilating, a probability of splitting again, probability of joining and annihilating, so it works perfectly. And we conclude that at large N, strings are free. By free, we mean They have no coupling. It doesn't mean they are trivial. It's still quantum mechanically very complicated. You still need to sum over the shape of the string. But two strings at large n, they behave freely. They don't interact with each other. Right? They quantum mechanically evolve in a complicated way. You still need to do all the planar graphs, which is still very complicated. But we back up this intuition that these graphs dominate over this. Now, of course, and this is string 1, this is string 2, this is string 3, this is string 4, and there are the other pairs as well that you could consider. But typically, if it was a realistic case, for example, you could force 1 and 3 to be in the past and 2 and 4 to be in the future. A very trivial way of doing this would be, for example, considering some complex matrix M instead of a real matrix, so that this matrix would have some charge. Then you could put some incoming charge that needs to be preserved, and you cannot just start flipping them around. Or you can give colors to this matrix and giving flavor. So you can decorate this a little bit such that you would have only one diagram. Otherwise, if they are neutral, you have all possible channels, which is also what we have in quantum field theory, right? When you do a 4-point function, you also have the 4 disconnected channels, which are just the directions where you look at. When you swap time, it's just crossing symmetry. So let's finish this analogy to see in one more simple example. How this would go. One more example, let's consider the interaction of 3 strings. Right, the connected parts. Now this would be like considering some interaction of 3 strings. But we should normalize it properly. Right? If we want to really say this is a normalization, I should make sure each one has one 2-point function. So I need to divide by the connected 2-point function to the power 3/2. Do you agree? This is the same as saying that each 2-point function is normalized to 1. And this would scale, well, each of these boys is n squared, so n squared, 3/2, and so in total 1/n. Which is precisely what should be the definition of the string coupling. Okay, this is just one more example, and of course, all these examples would work. Let me conclude with a maybe a small provocation, given that you just learned the planar limit. Maybe it's a little bit too early to already try to confuse you a little bit. But okay, I'll do it nonetheless. So if L is of order 1, we saw that this trace of M to the L, we want to identify this in our dictionary to a string. I did not say that L is of order 1, but I'm saying now. Now, let's think what would happen if L would be order n. Then we need to be a little bit careful, right? We always were drawing the diagrams assuming the operators were of finite size. We never considered operators that are of such big size, right? So we have to think a little bit, what would happen if L is of order n? Now, if L is of order n, you have an operator whose size is of order n. Let's see, so here, any diagram that would be non-planar was suppressed. So if I have this diagram here, let me draw it in green, this propagator that would pass on top of these ones and connect like this, that would be non-planar, right? This stuff here, where I connect like this, this is suppressed. Now, why is this suppressed, this diagram? It's suppressed because we lose loops. We lose powers of n. Do you agree? On the other hand, note that when you decide where is this propagator going, there are like order L options. Right? So if L is 10, there are more or less 10 bad diagrams that you don't consider. Okay, so even if you sum all of them, 10 over n goes to 0. But now that we say the size is equal to n, there is a competition. On the one hand, the diagram is suppressed. On the other hand, this diagram, there are L options where to connect to. Whereas neighboring graphs, you only have one option. You go to the left or you go to the right. So all planar graphs have this locality built in. That when you are drawing the graph, everything is local because you are drawing it on the plane. When you go non-planar, you get non-local. So you get extra factors of volume. So if your graph is very big, even though the diagrams are suppressed, because the entropy is so big, there are so many options to connect, they are also important. So when we conclude that when L is of order n, now higher genus matter as well. And in particular, when you have a string, it means that this correlation function of a string to a string is much bigger to a correlation function where a string breaks into two. But now, when L starts to be of order n, if you consider this very big, here L is of order n, and you consider this big two-point function, you can convince yourself that this is of the same order as a two-point function where you would actually emit a small closed string. Whereas these guys are big, and this is big. And this would be of the same order as the diagram where you emit two small closed strings. Right? Again, I'm saying that I have m to the capital L that scales like n, m to some L prime that also scales like n, could be L. And then these guys are of order 1, and all these graphs are of the same order now. Whereas here, no, this was much bigger than this, that was much bigger than this. And so what happens is that when L is of order n, this object now is a good object that sources closed strings. It becomes an object that has no problem producing closed strings. And what object in string theory is the source of closed strings?
Brain?
Yeah, D-branes. And so the idea is that as n becomes large, these type of objects, the proposal, the guess, again, this is just a tentative dictionary, is that these guys will now correspond to branes. Branes are objects that like emitting strings, that are the sources of strings, like charged point particles are sources of electric field. And what if L is of order n squared? Well, now the higher genus dominates. You want to produce strings. It's the few strings that are suppressed. Now, this diagram is much smaller than the diagram where you emit stuff. Because there are so many options to choosing emitting stuff, and higher genus are enhanced. So now you have an operator that you put, and it wants to create infinitely many closed strings. Right? So what object in nature you put that wants to produce infinitely many closed strings that include infinitely many gravitons? It can be anything that is big enough to deform a geometry. Right? If it's an object that is so big that you should describe it as a coherent state of infinitely many particles, like a geometry. A geometry is what? Is a coherent state of many, many gravitons. It can be a gravity wave, it can be a black hole, it can be anything. But it's an operator that is so heavy that is deforming the geometry. And so this operator would be a geometry, these operators would be geometry deforming objects. Like black holes, like gravity waves, like any object that is so heavy that it back reacts on the geometry. And that's indeed the kind of objects that we have in string theory. In string theory, we have strings that are just probes, light objects that move, d-branes that are heavier. They are still probes, they still barely deform the geometry, but they are heavier. They are now planes that can source closed strings. And if you put many d-branes, like stacks of d-branes or other objects that are even heavier, now they become very heavy and they can deform the geometry, and they would be things like this. And all this, just this large n counting, gives us some intuition that this object should exist and so on. Okay. So this would be a good point to stop. And next week, we try to put all these things together, ADS, large n, and so on. And we will get finally to ADS CFT.